So welcome to the first talk of the day. We have Uri Bader, quantum superposition of Maryland and Weizmann, telling us about higher property T, Banach representations and aggregation.
Thank you, Man.
Yeah.
And I want to thank the organizers. This is a wonderful event, and the audience is fantastic. The lectures are fantastic. It's really a pleasure to speak here. I will talk about higher property T, which is some sort of an emerging, it's related, maybe classical point of view on this emerging subject of high expansion, which is very fascinating. And I cannot not make a comment that today is a special day of some optimism, nothing to do with this conference, but after some time. But back to the talk. So this is, as you notice, I will try not to make a fuss of this, but it's a wonderful, it's a pleasure to have this joint work with my co-authors. And let me start with the definition. I would say gamma here, it could be G. Gamma, of course, is countable group typically. G is locally compact. I will state the definition, the simpler one for gamma. And I will say that it has the higher property T, the higher nth property T, if for every unitary representation, so this means gamma goes to the unitary operator on some Hilbert space, and since I'm using cohomology all the time, I don't denote it by H. But V is typically a Hilbert space, sometimes it will be a Banach space. So for every such, Hi gamma V equals 0. For I less than A. And there is a companion definition. I would say that gamma has Tn with parentheses. If this is the case, under the extra assumption that there are no invariants in the representation. And this makes a difference. It's not the same property. And examples, what you should have in mind is simply groups and their lattices. They have T up to the rank or higher. And this is a result by myself and Roman. So the first part of the talk mainly will be about results by Roman and myself, and later on we'll go to the group of 4 authors' work. Now, over a non-Archimedean field, we actually get the bracket one. And not higher. And this is the result, let me put it here. This has a long history. This was actually before. Okay, so maybe I'll show example specific. So SLN R, SLN Z. They have T n minus 2, not higher. SL and QP. This is the non-Archimedean field that's there. This has Tn minus 2, and these do not have, for n high enough, the bracket thing. So these are indeed different. And just reference here. So following the work of Garland, there is a work by Dimara Januszkiewicz. I will not title the name, the lecture for that. And this, so they did it when P is large enough. But really, I mean, the final goal here in this theorem is by Greenbaum. This is not well known, it should be. Greenbaum raises and Oppenheim. Okay, so these are the examples. I'll make some trivial remarks, and then I'll develop the subject a little bit more and expand towards Banach spaces eventually. Questions so far?
So it's not higher for selenium, it's maybe higher
For example, you know, for SPN1, while it is rank 1, it shouldn't, but it does have T.
and for high rank.
And SPN2 doesn't only have T, it has T2. No, it shouldn't, so I mean, in some sense. In the PID case, you don't have such things. And this is a very, very interesting subject, and I can talk about this more, but this is not the subject of my talk today. Today I'm talking about what happens up to the rank, basically. But it should be explored more. And maybe I should mention that we do exploit more with Yuval Goffman and Michael Glasner. There is a beautiful subject here. Okay, so I'll make some remarks. First of all, as I already kind of pointed out, the degree n equals 1, these two definitions coincide. It doesn't happen typically in higher degrees. So I will just denote it property T. I mean, there is a fast shell when we denote property T. Should we do the parentheses or not? So for me now the standard is just T is either T1 or with brackets or with parentheses. And something that we all know is that, and I want to emphasize, is that T implies final generation. I want to emphasize it because we do not know if higher T implies higher finiteness. We do know that Tn for whatever n does not imply, even the strongest property, does not imply finitely presented. So when with Roman we put the first paper on the subject on the archive, Kashdan asked me this by email, so I'm very proud. He cared. But we still don't have an answer here, and I'm emphasizing it because we are about to assume this. So, not here.
Sorry, what's the meaning of the question? Isn't finite?
Okay, yeah, so I'm about to explain, I'm emphasizing it because I'm about to assume higher finiteness for simplicity, and so I'm about to define it. It will answer, I mean, so higher finiteness does not implying finite presented. I'll put it here. So we are about to assume throughout what is called FP infinity Q. I mean, this is just for simplicity. And this means there exists projective resolution for the trivial model of finite type. So, and, actually, I'm about to take it free. There exists a resolution Q, Q gamma of 3 modules of finite rank. So the thing is that the powers here are finite. Call it di, such that this this sequence is exact.
Does Dn pass proportions?
Yes. And this one is called the boundary map, the ith boundary map. And what I want to emphasize about it, it already was mentioned in the Piotr talk. But nevertheless, just recall, this is an element of matrices, space of matrices over the group algebra. And moreover, we can make the formal adjoint. So it's a map here. I will not write it down, I will just recall. What we can do is taking the transpose of the matrix and apply the conjugation on the group algebra, which is just inverting the group elements. And completely linearly. What's that?
Shouldn't the error of the adjoint be reversed?
The error of the adjoint should be reversed. Yes, this is. Thank you for that. But now also I can make one extra guy. Again, was discussed in Piotr talk. This is delta. Let's get it right. I'm having here delta I. So this is an element in M and I square matrices over the group algebra of special importance called the Laplacian. And now I'm about to quote a simple lemma for homological algebra. That has nothing to do with the property T thing a priori. It's just assume we have an extension of unital algebras. And assume that these Laplacians, when I view them over this extended algebra, are invertibles for, say, y less than n. Then we get that for every A module, both the group cohomology and the group homology vanish for those i's. Vanish for those i's.
Sorry, what's an extension?
I mean, this is just an algebra.
Inclusion.
Well, yeah, this is inclusion. This is just a bigger algebra. I
It's an
mean,
injective map.
it's a, yeah, it could be non-objective, but yes. It's homomorphism function, unital homomorphism function. And this is relevant because of the following. Maybe I should emphasize this map over here. It's called the augmentation map. Just the map that is given by summing the coefficients of a linear expression, of a linear combination of group elements. Right? I mean, assign to every group element the value 1. So we always have this augmentation homomorphism, And this rotation homomorphism extends to the enveloping C-star algebra. So we have here C-star. Sometimes people write max over here. This is the enveloping C-star algebra of gamma for me. So I will not write down the definition. This is the C-star algebra that is defined by the universal property that for every unitary representation of gamma, extends canonically to this to a star representation of this C-star algebra. Okay, so we always have such, and we always have the extension of the augmentation homomorphism over there, which means that basically this comes from the fact that every unitary of representation of gamma contains a trivial representation of gamma, which is actually a map to C. As you see, I care about unitary representation, but in a sense I care more about unitary representation with no invariance. So I care about the kernel of this homomorphism, which I will call I star gamma. So this is the augmentation ideal in the C-star algebra level. Now, we already seen.
What is this epsilon?
Oh, augmentation, just gave it a name. The trivial representation. The trivial representation, thank you. Already mentioned in Cornelius talks, maybe in Piotr's, that if we have property T, then we have Kashdan projections. Then this means that actually we have, I mean, this sequence of algebra splits. So C star gamma is a direct sum of this ideal and an ideal associated with a trivial representation. So under assumption of property T, I star gamma could be seen as C star gamma modulo the Kashdan projection. And in particular, it is by itself it's a unitary algebra. I mean, it could be this A over there. And what is it really? How should we think about this algebra? This is the universal enveloping algebra of all unireps with no invariance. Okay, so under the assumption of property T, we have such universal object that kind of separates the world of all unitary representation and the world of, I mean, and the single trivial representation. There are, as you know, by definition, more or less, if we don't have property T, these two worlds are not well separated. So this algebraic statement, this unitary algebra, really is the statement that we can separate. And it follows from my work with Roman and also earlier work with Piotr that already he mentioned, basically that Tn now is equivalent to having all these. Oh, so maybe I should say, from now on, I'm going to assume property T most of the time, so I'm taking I star gamma not as an ideal merely, but as a unitary algebra. So you should have this in mind. So I can think of these elements over here, and Tn means that this is invertible for those i's. So once having this, we put the following lemma. So I should say, I mean, many things that I'm saying now are actually quite trivial given the setup, but it took us lots of time to observe, and many things that are kind of new, and our picture of this entire subject changes by the day. I'm getting clearer and clearer. Sometimes more obscure, but most of the time clearer. You know the phenomena. So, so again, this is the lemma that we proved with Roman. And this is some sort of an algebraic characterization of higher property T. So for gamma, will not state all the decoration here, but Tn is equivalent to Hi gamma with coefficients in this algebra vanish for small I, plus a little extra at n plus 1, this cohomology is Hausdorff. Maybe I should say a word, it was already mentioned, but we are looking here at continuous cohomologies. This cohomology with unitary coefficients. Cohomology is the quotient of the cocycles, which is always a Banach space or a Hilbert space in this situation, under finiteness assumption, modulo the boundaries, which is the image of a continuous operator that might be non-closed. So the quotient space might be not a Banach space or Hilbert space by itself. Just 1 minute. So if the boundaries are closed, then the cohomology is a Hilbert space by itself, and it is Hausdorff. Otherwise, the zero element in the cohomology is not closed for the quotient cohomology, is not closed for the quotient cohomology, and this entire space is not Hausdorff. It could be, however, Hausdorffified, and then we call it usually the Hausdorff cohomology or the reduced cohomology. Already was mentioned. Yes, please.
In that statement, Hn plus 1 is with coefficient in I star gamma.
Yes, same coefficient. I was just lazy.
You said Hilbert spaces.
Yes, okay, Banach space. Yes, thank you. It's a C-star module over this C-star algebra, really. And one extra equivalent condition, same in homology, which apparently is slightly better suited here, because I don't need these extra conditions. Because in homology, the arrows points there, not there, and nothing could happen in the highest degree somehow to make my picture less clear.
But don't you want to say that H0 is Hausdorff?
Here, no, this is, I know, make a remark. I mean, there are various equivalent formulations, and I choose this one.
This is under the assumption of property T. This is a standing assumption.
This is an equivalent formulation for Tn. No, this is, okay. I kind of assume in my discussion property T, but actually this is not, I mean, this equivalence is not under the assumption. If we don't have property T, in degree 0 here, we will get a non-trivial space. In degree 0 here and in degree 1 here. So,
Assume finite generation.
I do assume finite generation throughout. I am assuming in this discussion finiteness properties as appearing there. I mean, I need it up to n. Yes.
Okay.
And if I write here, you see? No. I will write here and lift right away. I just want to make the remark that, I mean, same for Tn, replacing I star gamma by or with C star gamma, somehow allowing also the trivial representation, and then you pay a little price, and then you want H0 gamma C star gamma. It is not 0 anymore. Then it is one dimensional. Now you can see, I hope. So we have similar equivalent definition in that case. Questions? So what I'm going to do now is basically I want to go to Banach spaces soon. But before this, I will show you a little lemma just to see how things behave, because it will also will serve me in my discussion in the future. I need to calculate my time. Yes, I think I'm good. The t-index, the n over there, is sub-additive or sub-multiplicative. So what I'm trying to say is that if you take a Tn group and take the product with a Tm group, you get a Tn plus m plus 1. Actually, what is sub-additive is not the n, it's really the T rank. We will not change the definition now, but the T rank is the first index where you have non-vanishing. And this is something which is additive with respect to multiplication. So really what I need to show here, to put here is plus 1. And this is not accurate. So I put a prime, this is meaningless, but this is just a slogan. This is almost a statement. I'll now explain what I mean by this. If gamma as Tn and lambda as Tm, and you are giving me the product and a unitary representation of both. And this is the prime now. I want not to assume, just not to omit the trivial representation, but also the relatively trivial representation. So I want to assume that none of the factors have invariance. Then you get, what is supposed to be Tn plus n plus 1. So then we get vanishing of cohomology with these coefficients for those i's. And it will be very easy for me now to, I have the language to explain it very easily. If you are experienced with the machinery, the miraculous machinery called spectral sequence. Otherwise, you can shut down for a minute and ignore. But so this is the statement. Now, this guy here, how do we compute this usually? We look at the mixed cohomology. When we take the pth cohomology of the qth cohomology of lambda in V. One more. And if these are all 0, when P plus Q is, is I, which is less than n plus n plus 1, then I'm happy. And this is indeed the case. And why is that so? This condition here really means that either P is less than M or Q is less than M. And now I only need to observe that this assumption here really makes this one, V, is an I star lambda module. So if this is the case, all these guys do vanish. And otherwise, I'm looking at this entire thing, and this is and V is an I star gamma module, and by the commutation of the action, this entire cohomology now is an I star gamma module. And if we are here, I guess upside down, this vanishes. Okay, so this is a little computation I made, and you should be convinced. And if I told you to shut your eyes because of spectral sequence argument, etc., we are done. We are happy with this.
Excuse me?
Yes, please.
So that if Q is bigger than M, that thing, like if Q is much bigger than M, say M plus 2, then it would not be Hausdorff.
Yes, this is a very good question, and we stumbled upon it. when you do continuous cohomology computation, you cannot use a priori spectral sequences argument without some assumptions, exactly of the houseofness of the cohomology spaces, etc. We used algebra here. This is, this is complete algebraic setup. I guess this is a complete algebraic setup, and we use that. In fact, there are way around the Hausdorffness. We had an argument even before with way around the Hausdorffness. It gets more complicated, but we could save it anyway. And in fact, this will come up in a minute. But this is an excellent question, and I want to emphasize that this algebraization of the property is really useful. There is another caveat that I want to emphasize. This is not true in case n equals m equals 0. I did use this characterization of I star gamma as an algebra, which holds under the assumption of property T. Now T0, or maybe I didn't clarify it, but T0 is all groups. T0 is non-condition, and if this was true for n equals m equals 0, it means that every product of every two groups is basically T, or relatively to this condition, which is absolutely ridiculous. So it is not true, and you see how it comes up. It's through this statement. However, and I do want to emphasize this, and this is a non-trivial statement, this is true. This statement over here, if n is 0, so gamma is arbitrary, completely arbitrary group, and m is not. And for this argument I gave does not hold, and we need extra work. And what Francesco said that is very much relevant. I will not envelope this work here, but it is crucial, because this is exactly the step. Okay, it's not too hard to see this, but again, I will not have the time to do. But the fact that when you take a group with Tn and multiply it by, or take the product with just an arbitrary other group, under the assumption that there are no invariants, you get extra dimension of T, extra degree of vanishing. And this is the ingredient that enables us to prove that for simple groups and lattices, we have T rank -1, which I emphasized earlier. And let me just briefly explain why. I'm not about to write down things, but I want to convey an idea. This proof, think of SLNR. And you want somehow to prove it using products, using this trick here. What we do is looking at all the Levy subgroups of SLNR, which is just SLK times SLK1 times SLK2, etc. When the Ki sum up to n. So these are the Levy. Actually, this is a semi-simple part of the Levy. The Levy itself has also some central thing, which is this gamma, the arbitrary n equals 0 thing in this thing. Somehow by a very intricate induction argument on Levy subgroups and working over a space called the opposition complex. Opposition complex is a companion of the Tits building. So Tits building is a space on which the group act, where stabilizers are parabolics, and it is highly connected. That's the Solomon-Tits theorem, there is a companion space called the opposition complex where stabilizers are Levy, and it also is highly connected. And the Levies are, by some sort of an induction argument, they have the right kind of property to think, and using this relation between these structures, we kind of able to prove that statement by induction. I would just say that this is really, it is currently a quite intricate argument because we need to go to group of finiteness properties, so we need to replace G by appropriate sublattice, and we need to have appropriate induction here, and we need to go and work with non-uniform lattices, so induction is more complicated, and also this opposition complex that is known to be highly connected. It's only known in some combinatorial level, and it's hard for us to use a continuous cohomology while doing this. So at the current state, we have a proof which is quite convoluted, and we are looking for improvement of this proof. Every now and then we come with a better, much more conceptual proof. The main advantage of the convoluted argument, which I'm not showing it to you, is that it's actually correct. So, but in the future, I hope to have a much better explanation. It's
When
you.
you take the product, you take the product T note, so this should be non-trivial.
Sorry, what?
You said if you take a product, a group is T times another arbitrary group would be T2.
Yes.
Arbitrary
T2
group,
prime.
what do you need?
You have this low invariant vector.
So yeah, you have to. So we need to work with a G representation, not a gamma representation, because we use how Moore that have no invariant to small subgroups, and then we maybe I'm not answering the right question. Okay, let me not go there for some obvious reasons, but I'll be happy to discuss this. But the thing is that eventually, in this intricate proof, we are not using this theorem. We are just using this part of it, because the induction always takes us just 1 degree less somehow. And this is slightly more complicated, less algebraic. Here I just showed you the proof completely. This is less algebraic, but it's more stable in a sense, because this is a very Hilbertian object, the I star lambda. That the I star gamma that I discussed is very Hilbertian. And this argument that we have here is more stable. So actually, a new ingredient is that we can now do it for Banach spaces, or at least for some Banach spaces. So now it's a good time to make the following conjecture. Maybe I'll take another one. Maybe you are already guessing what the next conjecture is, because it's kind of obvious in the setup of given previous talks in this conference. But I don't only state it for its own sake, but also as a platform for the next discussion. So the conjecture is that semi-simple groups, or simple groups, I mean, in this discussion, simple groups means simple Lie groups. So they have T rank -1. These are already proved, actually, already explained. But you see over here, this is uniformly convex. So given that we already had lectures, I will not write down more than that. I think this is self-explanatory in our context, but I will say it. This means that we have vanishing of cohomology up to rank -1, or below the rank, when coefficients are not merely Hilbert spaces, but arbitrary uniformly convex spaces with isometric actions, and parenthesis means no invariance. Okay, so this is a conjecture. It is natural in our context, but why do I emphasize this? Because actually we can prove it in some cases, and this is what I want to emphasize. So let me just recall that we have this Oppenheim, and I cannot help it, but right, Saleat, it's not meaningful to most of you, but this is drive slowly. This is the Lat and the La Salle. And they proved that, well, they proved this conjecture in degree 1. As in particular, let me phrase it as this, SL3R has, they proved it in degree R for high rank groups and lattices, as just T. And I mention it also because I want to make a further conjecture, which is the following. If we have such a thing, SL3R, and we have a map to the isometry group of a uniformly convex space, and no invariant, then not only what follows from here that SL3 does not have almost invariants, but I want to, I'm guessing that also the SL2R block inside SL3 has no almost invariant. No almost invariant. So it has a spectral gap. This is something that we know for Hilbert spaces by relative property T. I mean, it's okay. It's not the usual formulation of relative property, but it does follow. We don't know it in general. These guys' proofs does not hold in this case. But what I want to emphasize,
So SL2R has what? I don't
and
understand.
no almost invariant vectors.
So the conjunction is you have a, what's the arrow? Is it just
For every such representation,
so G is SL3R?
G is SL3. Yeah, I mean, this is just writing quickly that there are no
Then you
invariants.
have a uniformly convex, what?
Uniformly convex Banach space.
Okay.
Yes. I would use the term typically super reflexive, but it was not mentioned in this conference yet. But this is basically the same thing. Now, the thing is that this conjecture implies that one. And this is what we did with Shaketsar and Roman. We show that this implies that. And as I already said, this conjecture, I mean, it's not only that this conjecture for all spaces implies that conjecture for all spaces. For every particular space V, if we knew that, we can prove that.
If you know it for SL3R.
If I know it for SL3R only, yes. Well, for and SP4.
Okay.
Yeah, but thanks. I mean, I'm being a bit brief here. Yes, I mean, if I knew it for SL3R, I could prove this for all SLN and most other groups as well. I need to know the version for SP4 as well, to do it in general. So this is particular conjecture, but the thing is, as I said, we do know it for Hilbert spaces. So this little thing here, the proof, the new proof, already gives a new proof for higher property T for simple Lie groups, but it gives more. And this was already brought up. Basically, I mean, I will write BFGM with Fuhrman, Geland, and Monod, but it is almost a triviality. We don't know this. I mean, once we do know it for Hilbert spaces, for unitary representation, for L2 spaces, we can transform this non-invariant or this almost invariant, etc. We can transform it to various other spaces. This is true for LP spaces. So this means that also this is true as well.
Including one, which is not uniformly convex.
Yeah, okay, I'll make a remark about one. Yes, I'm about to state what I know and what I don't know about one. But let me give some respect to the corollaries here. Simple groups and lattices have T rank -1 for LP spaces. Notation, I hope, is self-explanatory. And yes, to Ramon's question, it follows from the discussion that this works for P more than one. The equation here needs some extra work, and it uses ideas from another paper of myself and Gelader and Monod about L1 spaces, but it doesn't use just the result we have there. We need the techniques also. So, so the case P equals 1 is a bit intricate, but I do want to emphasize it because it has very nice corollaries that I want to now write down. So here's another theorem of ours, which I think is of independent interest of all the entire story that I'm telling here. It's an analog. We all know, I think, that property T groups have this fixed point property when they act on trees, property FA. So we have a higher dimensional analog, higher degree analog of this. So if what we need is not property T itself, we need the L1 version. So little L1 here, which is implied by big L1. If n is 1, we know by BGM that this is the same as the usual property T, but in general this is a bit different. If we have this, then every action on a contractible simplicial complex of dimension at most n as a finite orbit. So when you combine the arrows here, you see that we prove this for higher rank lattices. So in particular, let me emphasize, this is Farb's conjecture. High rank lattices have, it's called FAN. It's a variant of what I wrote before, rank minus 1. FAN means fixed point for actions on CAD0 simplicial complexes. So we have it. So Farb proved it for various lattices, always non-uniform lattices, because he used unipotence. His result was kind of algebraic, or uses the growth of unipotent elements in lattices, and now we have this cohomological setup which also work for co-compact lattices, cocolat. Another thing that follows from our work, and reaching the end of my time, so I will be brief, but this is important because it was conjectured by Gromov about, again, for G and lattices, it's about the LP cohomology. The LP cohomology, so this means looking at the usual cohomology. It could be defined in many ways. The way I want to think about it is about the cohomology with coefficients in the regular LP representation. It has the following properties. It vanishes below the rank. So this is what follows from this vanishing result in LP cases. And actually, this is our contribution. I'm about now to summarize things that were known before, or maybe the following is also our contribution. It's Hausdorff at the rank. And non-vanish for pi enough. So this is by Bourdon-Remy. Maybe I should say that the entire subject is a lot. Pierre Pansou made lots of contribution to this and make this entire things also even possible. But Bourdon-Remy proved these things. And also, it does again vanish vanishes above the rank for pi enough. In fact, my time is up, so I just say it very, very briefly. In the non-Archimedean case, this actually holds for all p, this and that. And this is by the work of Antonio Lopez Neumann. And I cannot help but make the remark that it seems that when P gets high and high for the symmetric space, it gets, from an analytic point of view, it gets to be looked more and more like a building. And in particular, anyway, this is Gormov conjecture. We proved it. We are very happy. This work is just pleasure. Thank you for listening.
Questions for Uri?
So towards the beginning you said that it's not knowing if higher T implies higher finiteness, but you also said that higher T does not imply finiteness.
Yes.
So what is that? Is actually the thing you're asking?
So I know that property T does not imply finitely presented. Let me maybe make the following remark, which is interesting. I think you can look at SPN over the p-adics, and this has property T by what we said, higher property T. But also it still has higher property T if I take a semi-direct product with the Heisenberg group. But now this guy is not compactly generated anymore. And also lattices in it will not be finitely compactly presented, I meant to say. Lattices in it will not be finitely presented. And these have, when n increases, you have as much higher property T as you wanted. So finitely presented is not implied by property T, but what one would suspect is that this property over here might be implied. And this is what I meant.
With infinity replaced by n?
With infinity replaced by property T, yes. I mean, property T just implies finite generation, definitely not finitely presented, but also not FP2. So the analog of this might hold, we don't know. And in this discussion, we did assume it, and we did use it in the proofs, and luckily, for lattices in Lie groups, we always have the FP infinity thing, so everything is fine. And somehow also maybe mention, I think this is very interesting, the entire theory of cohomology, continuous cohomology of locally compact groups is not yet enough developed with regards to finiteness properties. We understand quite well finiteness properties of countable groups, but not of arbitrary locally compact groups. There are several attempts to understand better, and I could imagine that there will be progress on this in the near future, because this is very interesting and seems to be doable. So I think there should be. It should be done. And this, again, this somehow forces us, this one of the reasons that forces us to zigzag in our proofs between G's and gammas all along. Even when we want to prove things for G, we have to take cocolat init gamma and to, or sometimes non-cocompact lattice, and discuss its properties, etc.
Is it it possible to explain why higher cohomology can be used to prove a fixed point theorem, like for the...
Yes, it is possible to explain. I choose not to focus on this in this talk because it's a non-trivial argument, but I'll give you the framework, which what you want to look on is some sort of a double complex. Again, we had a spectral sequence argument. You can do it by some spectral sequence miracle, but actually in this case you can do a more pedestrian diagram chase thing, but you need to do a diagram chase. The thing is that you look at maps from gamma to the p. So gamma acts now on x, and this is a simplicial complex. So you look at maps from gamma to the p. This is the thing that computes cohomology usually, but now you take coefficients in the group generated, the space generated by the Q cells in X. And you get a double complex here. And okay, I will not perform the argument, but the thing is that you do diagram chasing on it. Using the fact that X is contractible, you get some information. And then you complete to L1, and the fact that all the arrows are still continuous when you do this really needs the L1 here. It does not work for LP. Sorry. Here, yes, thank you, Roman. The fact that all arrows are continuous needs the L1 condition, and this is why I emphasize that this don't maybe too much. And then we use the properties of vanishing of cohomology of gamma and compare somehow. This is in 2 sentences, the reason for why it holds.
All right, so we have maybe, because there's just 3 minutes for the next talk, so maybe we can stop here and take further questions to T after the next talk. Okay, thanks a lot, Uri.